Hauke Zachert from Darmstadt Technical University. So the floor is yours.
Yes, thank you. Welcome to my presentation. I'm Hauke Zachert from Technical University Darmstadt, like Marco said. Microphone. Okay, so now we start again. Okay, so yeah, welcome to my presentation about the high cycle accumulation model for sand, its fundamentals, applications, and challenges. So it's a work, or the presentation is put together with my with my colleague Jan Maracek. So we heard a lot already about offshore wind turbines, and of course they are subjected to cyclic loading. We heard now two presentations dealing with earthquake loading, but I'm going one step back, let's say in history, and look back on the cyclic loading, so on the normal cyclic loading. So what is needed there? We don't only want to design these foundations for the ultimate limit state, but also for the serviceability limit state. And for that, we need a proper simulation technique for this high cycle loading. In addition, we have so many different structures, like Yannis was also showing it to us. So we have monopiles, 80% of the market, but still we have jackets, we have suction buckets, or they are coming. We have some gravity-based foundations, not so many. And now, more recently, those anchors for floating structures. So we have different types of structures. And all of these structures are faced with new sizes, dimensions. We see that the monopiles are increasing to now 12-meter diameter. We have different loading conditions now with climate change leading to higher, stronger storms and so on. And also new foundations are developed. So I'm in favor of having a proper soil model, being able to capture this in terms of a mechanical model for the soil and not having specific engineer models, let's say, simplified models. So that's why I want to discuss, or want to show you again the high cycle accumulation model, which was developed by Muniz and Wichmann. And why am I showing it? Because I really spent a lot of my time working with Wichmann on that. And the same is true for Jan. And yeah, so what is this high cycle accumulation model? What do we need it for? If we try to model this high cycle behavior, then with a classical advanced soil model, then we will have high computational costs. In addition, I would say all of the models, existing models, have severe limitations. So they will not be able to really capture this high cyclic behavior with the strain accumulation. So they will rather model something like this, so a constant accumulation or no accumulation at all, it depends on. Yeah. And in addition, if you model hundreds of thousands of cycles, you will accumulate numerical errors, which is not negligible in such a situation. So what we see so far, and also what was presented here in the first two presentations, is that, of course, we aim for simplified models, which enable us to model such a system in an efficient way. So we all know the PY curves, yeah, and they then are improved based on model tests on high cyclic loading. Then we end up in the PISA model with some more things. We have macro models, stiffness degradation models, etc., etc. Many of them are valid or are calibrated on small scale model tests, either 1G or centrifuge tests. But I really want to ask the question whether I could really transfer a 1, 2, 3, 4, 5 centimeter pile to a 5 to 10, 12 meter diameter monopile. I think there are some aspects which needs to be considered. So I'm in favor of having a proper soil model, because what you can do then is calibrate your soil model based on the experiments you have, and then from that go to the real scale situation. So the other advantage is that you can apply this soil model irrespective of your structures. So gravity-based foundation, suction caissons, or even a shiplock, yeah, which also has the cyclic loading. So you are not bound to a monopile or whatever. You can apply it to whatever you want. For example, an embankment with a traffic load can also be modeled with this model. So in this presentation, I'm going to briefly go to the fundamentals. So have a quick look to the equations. I'm going to quickly talk you through some applications and validation, and this is more like a slideshow. So if I trigger some interest here, then just come to me and I can send you the presentation as the paper on that. So I will not go into details for all these applications we have, but I will also ask some open questions in the end and show you some challenges which we still have to face, or which we are still facing. So let's go to the fundamentals of this high cycle accumulation model. It was developed by Nemunis and Wichtmann in Bochum, and then they moved to Karlsruhe, and this is where I joined them. And yeah, so it's based on drained cyclic triaxial tests and a hell of drained cyclic triaxial tests. So on the left hand, you see a high cycle test device in Darmstadt, but of course, Wichtmann has many of them. And the basic idea is that you have a proper drained cycle with a constant stress amplitude, and then you get this strain accumulation. And the high cycle accumulation model aims to model this trend of this accumulated strain, and this is what it aims for. And so it's calibrated on hundreds of these cyclic tests. And here, for example, you have two of those test series, one with different strain amplitudes, stress amplitudes, and one with different densities. And based on that, then Wichtmann got these equations. I'll come to these equations later. So the idea is now to, if you have such a classical high cycle path, you replace these high number of cycles with a constant stress amplitude, with a constant load, but you apply this high cycle accumulation model, and this then allows you to model this strain accumulation. And this strain accumulation now it's like a creep model. Yeah. So what you combine here is a stress rate combined with the stiffness and the strain rate, but the rate is here. Material are you talking about? Sand. We are talking about sand and clay. Right now we are talking about sand, but the same model is also available for clay. Yeah. So it was in the title, but maybe I skipped it. The strain rate is connected to the strain rate is connected to the stress rate, like we know that, but here rate is in terms of number of cycles. Yeah. And so from there, you see here this accumulated strain. This is somehow the core of this ACH model. And this accumulated strain, we have there also, of course, a flow, let's say a flow rule, but it's not a flow rule. It's just the direction of the strain accumulation. And the hard is then in the end, how do we determine this accumulated strain in relation to the number of cycles, in relation to the strain amplitude, so how much strain do I have in the model, of cyclic preloading, mean effective stress, average stress ratio, void ratio, and polarization changes. So if I change the loading direction also, the accumulated strain will change. So you see that there are some variables here. And of course, the nice thing is now that once you normalize your accumulated strain with those factors, then you get a more or less homogeneous area where your accumulated strain is for all those different types of tests. And so in this case, in this way, you have your material model. Yeah, and of course this comes for a price. The price are some material parameters you need to determine. And here you have the material constants in this model, and here are some functions for that. And how can you get those? There are three approaches developed by Wichtmann. So the first one is you do 11 drained triaxial tests, cyclic triaxial tests. So this is the full-blown approach. You can also have a simplified approach where you only need one drained cyclic triaxial test, and the rest is done with correlations with the grain size distribution curve and your void ratio. And this also gives very good results. So you are not losing a lot of accuracy here in this case, and one drained cyclic triaxial test is not too much to ask. And there's also an approach with purely correlations, but this, of course, has some limitations in terms of accuracy. So this is basically what was already developed in 2005, and then applied and improved over the past years. And still there are some improvements. One is the strain amplitude. So typically what we need to do in such a simulation is we have to have two regular or two standard cycles we calibrate or we simulate with a normal constitutive model. So we typically use sunny sand or hyperplasticity with intergranular strain. And in this model, you determine the strain amplitude. So for each and every element, you get its specific amplitude of strain with a specific stress level and the void ratio, etc., etc. And from there, then you can apply this high cycle accumulation model, because then you can predict the strain and the stress changes due to the number of cycles for each and every element. Yeah, but the problem is, of course, due to these accumulated strain and stresses, also your stress conditions change in your model. So, and that would then typically also change your strain amplitude. And this is, in the past, this required then a classical control cycle, again, with a classical soil model. But this is a little bit a disadvantage. So this was improved by Staubach et al. By applying an adaptive strain amplitude. So this is now not keeping this strain amplitude for the element as a constant, but it's including also the change of stiffness and density, etc. So this is a quite good improvement. And the other one is there's also a model available for clay, which is here checked against laboratory tests or small scale tests or centrifuge tests, sorry, on a soft clay, but it's this model is not the basis of my presentation today. Okay, so these were the recent developments, and now I'm going to show you some applications and validations of this model. Of course, we started with small scale model tests, so like we heard from earlier, that of course you need some data to compare with. So we started with small scale model tests in 1G, and this is a photo, and we were able to capture quite good the total deformations over the number of cycles, 10,000 cycles you see here, and also the accumulated strain. So this is the numerical simulation is the dashed line compared to the experiment. But we were not only able to look at the displacement, but also to the development of the bending moment, for example. Because we have a proper soil model, we can really, for example, here we have over the depths the change of the bending moment with the number of cycles. So this is for 1,000 cycles, this is for 100,000 cycles, we have the change of the bending moment. And if this is in the experiment, on the right-hand side, we have it in the numerical simulation, and we can see that even the values are more or less the same. So this was quite an encouraging result. We also did this for the well-known test from LeBlanc, back calculation. This is a more recent paper, and there we also evaluated how the installation effect is affecting this cyclic accumulation. We know that there's a lot of research going on about this, about the installation effect on the cyclic loading, but also the high ACH is able to capture this accumulation effect as this installation effect, sorry, as long as you keep the initial conditions right. Yeah, and this is shown here in this publication. We also checked it for a centrifuge test on a pi group with also reasonably good comparison, and this is just on the installation effect. So we are doing currently some work on that, because from my perspective, this is fairly not solved, how the installation effect really affects the cyclic accumulation. So, but going from this small scale or centrifuge test to a real large scale test. So this was a very unique test performed by Ed Süblin. It's a large scale foundation. You see it here. Here you see a small car. Yeah, so it's 40 times 40 meter. loaded with 1.5 million load cycles in under, let's say, almost offshore conditions. So it was fully saturated. And we also modeled that. Here we have the load diagram for the first 350,000 something cycles. And this is the first storm package. And you see here it's a load with up to 10 meganewton. It was loaded. And here is the comparison of the settlements of the individual plates. You see here this foundation is founded on 4 plates. And you see here the comparison of the experiment in blue with the settlements in red of the finite element simulation. You see a fairly good comparison, considering that we have really such a complex situation here, such a complex foundation, and also considering that the result of these finite element simulations were not back calculating it, but it was really, okay, taking the data from the field, doing a proper calibration based on the laboratory tests, and then doing a class A prediction. Okay, we knew the results, but nevertheless, we did this an honest prediction. So I think it's a fairly good comparison. And what was really interesting was that we also looked at the stresses below these plates. And what we found in our numerical simulations was that these stresses change after construction. This is what we see here. And then after the first load group, before the first loading, and then after the first strong storm. And we see that the loads are changing from these 2 plates, which are in the loading direction, mainly to this plate here. And we went with this result, we went to Zyplin and asked them, okay, do you see the same in your experiments? Said, we haven't looked at the data yet. There are so many data. So they looked at the data and this is what they got. Yeah. So, and this is the measurements, this after load group 1, this is directly comparable to the simulation. And I'm sorry, there's a bit different color coding, but here you have 350 kPa. And here you also have 350 kPa. So not only the trend was simulated, but also really the real numbers. And you can see here that even so after 16 storm events, it was even that severe that those 2 plates, B and D, are bearing the majority of the load of this foundation. And this was really severe because the foundation was not designed to bear all the load via this girder here. So in the end, this made them redesign their foundation to have 3 legs. The beauty of having a proper soil model is now you can, of course, also, first thing was we were able to predict this without knowing it in advance. And we can also analyze it and really show and explain what is happening here just by data, not just by guessing. What we see is, I mean, it's a bit obvious. These 2 plates here get the highest strain rate. So this is the strain amplitude under these 2 plates, so A and C. And you can see a large area with large strain amplitude. And these 2, of course, they have a much smaller load amplitude. So of course they get a smaller strain amplitude. And in the end, here the load, this soil is, here the strain is accumulating much more. So they are simply reducing the load. So that's why you have this rocking behavior. So once you know it, once you realize it, it's clear, but they were not thinking about it in advance. So has it been applied to practical projects so far? Not to my knowledge. Yeah, we are pushing for it, but I'm not sure whether it has been applied. I don't think so. But for example, here in the offshore wind projects in the Netherlands, you have. I have another time. In the offshore wind projects in the Netherlands, you have the sites. So the Dutch government is pre-developing their sites. So they have they put all their data online for all the wind farm sites, and so have a look there. There are really 10,000s of data, measurement data, and what there is, you have specific technical notes, for example, on drain cyclic triaxial testing, and this is why this is because they want to enable the developers later on to use the high cycle accumulation model, so that at least that they have sufficient data to use this model. So it's on its way to the practice, but to my knowledge, not applied so far. And here we also come to one of the challenges, because when we wanted to do that, one of the major offshore contractors really had severe problems in performing drained cyclic triaxial tests. They always had these poor water pressures here in each and every cycle, although they were supposed to be zero, and it's about 10% of the stress amplitude. So it's not negligible. So this is a challenge still in the commercial laboratories to have drained cyclic triaxial testing. Then another question is, how do you determine the cyclic preloading history in situ? It's not clear to me. And then the effect of pile installation, I already discussed this, but it's needed. Another aspect is the sequence of the load package. So this is really, doesn't matter in which direction you organize your packages. If you have multi-directional load package, so like these flowers here, so it will also change something. And then of course, currently we can only apply packages of constant load amplitude and average values. What if we want to apply an earthquake? So this is not something what the high cycle accumulation model is built for. Yeah. So what do we do in Darmstadt? I'm almost finished. We work together with Wichmann a lot. He's focusing on the model, and we are focusing on the implementation, the validation, and the application to practical problems of this model. So, for example, to perform specific tailored experiments in our large-scale pit to address the challenges I just has shown, and also to make the model available. This is via the software NumGeo. You can easily download this software. It's a finite element code, freely available, and it has this high cycle accumulation model included. So it's freely available and you can just take it. And we hope that this will really help to spread this model and to make it applicable to researchers, but also to projects. Yeah. And so this is already my summary. I think we have a very versatile model here. Model parameters can be determined quite easily. It has already undergone some validation. I don't think we are ready with that, but it has really shown its applicability in several projects. And it is freely available. There's also one version on soilmodels.com. So there are some options to work with that. And then thank you for your attention, and sorry for being a little bit late.
Thank you very much, Hauke. He already addressed a number of queries in his final slide. So is there anyone in the audience willing to answer to one of those queries, or the other way around? Yeah. Would you like to ask any comment or any additional information to Hauke? One from online. Yes, please.
Hi, thank you for the presentation. There is very nice. One question maybe, although you already show fantastic prediction, but I'm a little bit, I was wondering, because for the calibration, you mentioned a lot about the attractional test, but for the field or for some industrial project, it seems they perform also quite many, like for example, the direct simple shear test, this kind of thing. And that means like for certain part of the soil around the foundation, the stress pass, different a little bit. How do you think that will affect the prediction or the performance of the model? And do you think we trust more on the actual test, or we should focus on the direct simple shear test? Like any recommendation for this? Thank you.
Well, I think so. On the one hand, the model itself is really based on these triaxial tests. Yeah. So if you perform a triaxial test, you have a clear path you can follow and to calibrate your parameters. I agree that there are some stress paths where you could look where you say that the direct shear is that the simple shear is clearer, is more accurate. But I personally think that here you need high cyclic loading, and you need high cyclic triaxial test. So I would rather do a high cyclic triaxial test than doing a high cyclic shear test. Yeah, because I think that's here you have better controlled conditions.
Okay, let's move forward. Then Mauro Munoz is the next one from